Please, okay. Please, you moderate, Alan.
Okay, great pleasure to introduce Sean Giblin, somebody I've known for a long time. I think we were PhD students at about the same time. He was in, I think it was Sheffield, wasn't it, Sean? Did you do PhD in Sheffield?
In Durham.
Durham, that was it. So Durham, he did his PhD at Durham about the same time as that I did my PhD in St Andrews. And so we've got 20 odd years of working our way up to professor together. I see that now he's been promoted to the International Condensed Matter and Photonics group, which is fantastic. A joint director, which is fabulous. Lots of administration and less time for research and science, which is always the way that these things go. But nonetheless, I have a sneaking suspicion that Sean's going to give a great talk on today, and I'm going to give the floor over to him.
Thanks a lot, Alan. Let me just share my screen if I can figure out how to do that. Oh, it says I'm Alan. You have to stop sharing apparently. Okay, right. Let's try again. Okay, let's see if this works. Okay, can you see my screen?
Yeah, we can see it.
Okay, perfect. Thank you very much, Alan, for the invite, and thank you very much, everyone, for inviting me to this workshop. It's a great pleasure to be here. Obviously, I apologise for not being there in person. We can blame, for once, it's not my fault. We can blame somebody else, so we're going to blame COVID. That's sorry, excuse me. Let me just try and get my laser pointer on. So there we are. So thank you for the invite, and I'm sorry I can't join for the entirety of the day, but I'm sure you'll understand we have small children to look after early in the morning. So today, I think this is a slightly different talk from what you've seen already, having flicked through the program. But today I'm going to give you a discussion on how we've measured the isolated magnetic susceptibility. And hopefully I will explain during this talk why I think this is interesting and why it's important to think about the properties of materials as we kind of like probe their behavior, even though traditional methods suggest that these things are all well understood. So this work's been carried out at Cardiff University under the guise of Dave Billington, a postdoc, and we've had some PhD students helping us and a fellow academic. A lot of the low temperature work has been done at the CNRS in Grenoble with Carly and Elsa. So this is a truly international collaboration. A lot of the insightful advances have been contributed by Steve from the LCN, and our crystals have been grown in Oxford by Prabhakaran. And this work has been supported by the European microkelvin and the EPSRC. So just a quick introduction into the background of how we came to measure the isolated magnetic susceptibility and why we were potentially interested in it. So my history, if you like, is in spin ice. And so for those of you who are unaware of spin ice is a titanate, basically, to a first approximation. And on each of these tetrahedron, so each of these lattice points at the points of the tetrahedron, we have a dysprosium or a holmium, so a very large rare earth magnet. So if you imagine UB is basically to a first approximation about 10. And what we find is that there's some highly anisotropic crystal field component, and this gives Ising-like an Ising-like spin system at low temperature. So what this means is that spins either point into or point from left to right or point out of the tetrahedra. So this is called the 2 in, 2 out rules. Okay, so this is just the ground state. But the reason why it's interesting is that this 2 in, 2 out ground state, it implies a macroscopic number of ground states. So essentially there's 16 per tetrahedron. So just to clarify, this is analogous to what happens in water, in ice, sorry. So in ice, if we consider here, we've got H2O, we've got oxygen ions, ones, and we've hydrogen ions. And our hydrogen ions here, you can see that 2 are close and 2 are far apart. But there's no deciding which 2 are close and which 2 are far apart. And so this gives you the so-called 0-point entropy at low temperature. So this is a polling 0-point entropy. And the reason why we're looking at spin ice essentially is that you can replace the proton displacement, so these positions near and far apart, with the spin configuration. So instead of being near and far apart, the spins point into and out of this tetrahedron. And why it's interesting is that people have looked for emergent electromagnetism. And so what I mean by that essentially is if you flip a spin, so imagine if we flip one of these spins here, this spin can propagate along a chain of these tetrahedron, and they behave as though they have a magnetic charge. So they have a magnetic Coulomb interaction. And this is what I mean by emergent electromagnetism. So a lot of work's gone into this over the past 15 years. So I'm not going to talk about this per se. But what I want to talk about is what, instead of having spins everywhere, if we take most of the spins out, we're left with a single spin system. And can we understand the properties of that? And the reason we want to do that is that basically in dilute spin ice, so instead of concentrated holmium and dysprosium, you take basically 99.9% out. And the reason why this is interesting is, imagine if you've got this Ising spin, so you've got a spin point in one direction. Obviously, this is like traditionally, this has been interpreted as being a classical spin system. So it behaves under classical dynamics. But basically, what Tomasello in 2015 predicted was that if you look at the ground state doublet, this spin can flip. And here we plot the ground state doublet splitting as a function of field. And what we find is that essentially this thing can, with a transverse component of the magnetization, this classical spin can flip. And so we thought, oh, this is an interesting thing to do because this is normally a classical system, and we can maybe look at some kind of like quantum dynamics. And the interesting thing about this time scale here is that this time scale is in the order of megahertz. And we've built some AC susceptibility equipment that can measure from like, well, 10,000 hertz up to a couple of megahertz. So previously, all the stuff you can buy commercially ends here, but we've built something that goes up here, and this allows us, in theory, to get into this regime. However, obviously, none of these things work out as anticipated. So let me just explain how we kind of ended up measuring the magnetic susceptibility. So the original goal was to look at this dilute behavior in spin ice. And the reason we thought this was interesting is that we'd seen evidence that with this, so here we have a tetrahedron again with spins on it. And each one of these spins is about, let's just say 10 MeV. So the local internal field for the 2 in, 2 out is about 0.81 Tesla. So this is a huge internal field, and there's nothing we can do to flip the spin, you'd think. However, when you have a spin flip, which is this emergent magnetic monopole, which you can get to by cooling because it's a thermally activated behavior, we flip a spin here and we get something that looks like a magnetic charge. But when we do this, the local field distribution changes from 0.81 to about 0. So at this point, all we need is some small transverse fluctuation of our magnetic field to cause the spin to flip. So remember, it can only flip 180 degrees. So essentially, we have this situation where we have a monopolar-like excitation, and we just need a small transverse field to flip it. Now, what we've previously done is we've shown that obviously to flip between -J and +J, or just flip the magnetization, we've got a tunnel splitting of 10 to the -5 Kelvin, and this is when the local 111 field is equal to 0. But if it's not equal to 0, obviously there's no tunneling probability. But if it's some small distribution around 0, the hyperfine field, which is fluctuating, so the nuclear component, can essentially bring the system back onto resonance, and it can flip from -J to +J. And bearing in mind, this is purely a transverse component. So the question we kind of got sidetracked with was, can the nuclear moments affect the dynamics of these monopoles? And we found some really interesting behavior. So bearing in mind that one is frozen in this ground state, you've got what you'd call a classical system. Really, so we found that this is in bulk spin ice. We found that our experiment was to do this. We zero field cool the sample, our field, as a function of time. So we are sampled, we waited, and then when we wait, you would expect nothing to happen because this thing is frozen in this classical 10 µb system. So we go from here, but some time 0 to time 1, and then we start to increase the magnetization. And so if everything was frozen, you'd expect no change in the magnetization as a function of time. And actually, what we find is that when we look at dysprosium titanate with 162, so this has got no nuclear moment, if we wait 10 seconds or 56,000 seconds, when we apply a field, so this is where we ramp the field and we measure the magnetization here, we see no difference in our data. So if you wait 10 seconds or 56,000 seconds, nothing. But if you look at dysprosium titanate of 0.67, you wait 10 seconds, 40,000 seconds, you can see the gap begin to open up from when we start to magnetize the sample. So what this is saying essentially is that we are waiting in our zero field limit in this region here, where we're doing nothing, we're just literally waiting. These things that are be frozen are flipping away. And we think that we've demonstrated that this is due to the nuclear moment. So this hyperfine coupling is bringing our local monopole excitations back into resonance, which allows them to flip their spin. And we can see this even more clearly in holmium titanate with a bigger moment. You wait 10 seconds or you wait 35,000 seconds, and you can see that this wait time has a serious impact on when the magnetization switches on. And we can see that when we compare all our systems, when we look at 162, which has got no nuclear moment, we see no increase in the weight when the field switches. But for holmium titanate with the biggest nuclear moment, it switches on. So what we're saying here really is that in this classical spin system, mu b equals 10, we can see a very small contribution from the nuclear moment making the spins flip. So there must be some local field that goes to 0. So this kind of like made us more interested. And so we thought we'd go and look at the dilute. We'd go and look at the dilute version of holmium titanate. So and look at the single ion dynamics to see if we can probe directly the tunneling. Now, this isn't without precedent, and a lot of work has been performed on single ion dynamics and lithium holmium fluoride, and we already know how holmium ions behave in a dilute environment. So specifically, you can see these 8 levels, these 8 peaks in the AC susceptibility, and what these are showing is that as you Zeeman couple, as you apply a magnetic field, you're Zeeman coupling the nuclear and the magnetic moments. And imagine if you had a ladder of energies, and these ladders, when you apply the field, are coming into resonance with each other. And then when they're at resonance, you get some transition. And we see that there's 8 transitions because there are 8, the nuclear moment goes up to 7/2. So it's important just the thing that we were looking for essentially is just to get an idea of these dynamics. We wanted to see these 8 peaks and track them with frequency to understand the cross relaxation in our 1% sample. And also we can see in the imaginary part, we see dips, which come from dipolar coupling between the holmium spins because they're not properly separated. And we also see these little peaks in between the main peaks. And these are from the 2 ion representation. So again, more. So we were expecting to understand this quite simply, really, in reality. Excellent, we thought. So we're looking for 8 peaks to look at the single line dynamics, and then we can talk about the tunneling of the magnetization. So this should be simple. And this was a measurement we did, and we see all this plethora of peaks, and we see 8 or 9 peaks, and we're thinking, okay, this makes perfect sense. But when we increase the frequency, what we found was we went from 8 peaks where these nuclear and these spin levels are interacting. We went from 8 peaks to 4. So this is in the real part of the susceptibility. This is in the imaginary part of the susceptibility. And this is quite a strange result. So at this point, we thought we'd better stop and try and understand what we understand by magnetic susceptibility. Because we didn't understand the signal, so we thought it was there was some precedent to actually think about what we mean by magnetic susceptibility. And we know that in the simplest terms, we can define our isothermal susceptibility via the canonical ensemble as just dm by dh. And this is the derivative with respect to the applied field of the moment and the probability of occupation of state. So this is just a Boltzmann distribution, and this is a magnetic moment. So our magnetic moment is d by dB. and our Boltzmann probabilities is a thermal component here and a partition function here. And from this, you can also work out the adiabatic susceptibility. But also, importantly, maybe 70 years ago, people had been trying to probe and trying to look at the isolated susceptibility. The isolated susceptibility is fundamentally different from the isothermal and the adiabatic, in the sense that you can define it as a derivative with respect to dMdh and pi, but it's not a free energy derivative. So it's not a thermodynamic probe, it's a probe of this value of p. So if these populations, if this population is kind of, if there's a population difference, you'd expect to see some finite value of Ki. What this looks like is you see that as you probe with a function of frequency, the thermal susceptibility gives way to the adiabatic susceptibility, which gives way to the isolated susceptibility. So what we're saying here is that you can access these state populations, either quantum levels, by doing a simple probe. And this is akin, if you like, to the dielectric susceptibility. When you increase the frequency, you decouple your probe from your spin system from your probe. Sorry, your spin system from its environment. So just the isolated susceptibility is not necessarily related to the isothermal susceptibility. It's not a function of the free energy. It's not. And basically, for fixed values of populations, and we've got two different states, I and J, what we're measuring here is a mix of these population states. So in theory, we have a quantum mechanical probe using a thermodynamic probe. So a quantum mechanical measurement, sorry, of our thermodynamic probe. So this is just saying that our isolated susceptibility is it's I and J, which is so these eigenstates mixing up in some of these isolated spin systems. So the question is, how would you go to look for an isolated spin system using susceptibility and get quantum mechanical probe? So we can do some fairly simple maths to work out the concurrence, which is a mixture of these spin up and these spin down states. And we can see that basically we can predict when we're going to measure our isolated susceptibility. And it's quite simple that we can see that our isolated susceptibility is a function of phi, which I'll describe in a second. You'll see that we have various peaks are avoided level crossings in Chi-T, in Chi-I, but these are much, much smaller than nominal values of Chi-T and Chi-S, as you kind of expect. So how do we probe this with our single ion material? And the idea is that if we have a spin ice material with a dilute holmium, so essentially we only consider one holmium here on this red ion here, and we'll consider this is called an apical spin. And these are our basal spins because we're in the plane of this tetrahedra. And a Hamiltonian, we've got a nuclear component, and we know that our nuclear moments go from -7/2 to +7/2. We've got some Zeeman term, and then we've got some splitting. So this is a transverse component in this direction, essentially, with respect to this apical spin. We can work out our energy diagram, and we see that we have avoided level crossings at 1, 2, 3, 4 fields. So what we're claiming essentially is that as we solve this Hamiltonian, we're going to get two solutions. We're going to get the situation where our 8 levels, MS and ML, they essentially, when we Zeeman split them, they will all come into resonance at low frequency. But at high frequency, what we're saying is the only thing we measure are these 4 red transitions here, and this is this perturbation. And what we're really saying is we can decouple our nuclear moment from our spin state. So we only measure the isolated spin state. So we don't have an admixture of MS and ML. We only mix MS and, between -0.5 and +0.5 when we go into this isolated limit, which corresponds to only to the avoided level crossings, not to direct transitions. So we can see that this makes sense experimentally, in the sense that as we increase our frequency, we go from numerous peaks to just 4 peaks, essentially. And what we're claiming here is that this is an admixture of our, at the avoided level crossing, just at this position here, we're measuring this the state population difference between plus and minus of our holmium ions, and our nuclear moment doesn't contribute. And we can see that as we measure our susceptibility as a function of field for low frequency and high frequency, we can just check that the peaks lie in the same place. So for 10 hertz, we've got all these peaks, and for 10,000 hertz, we only have 4, but they're in the same position. So this is good because it gives us, we can clearly demonstrate that this is related to the holmium moments. And we can then fit this isolated susceptibility to give a thermodynamic measurement of the state population. And essentially, what we find is in our real part of our susceptibility, 1, 2, 3, 4 peaks, and we can fit this perturbation. And we see that really, in reality, this is our theoretical value of chi, the experimental value. And there's several features that we should take into account. The first is that obviously we get the peaks at chi. It's kind of forced on us by the fact we've got this avoid level crossing, which is good. But we also see that we can't really describe the shape very well. So there's some kind of background. And also we should note that our chi double primed, our imaginary part, there's a small peak here at the second peak. And we think this is down to some small amount of clustering and the fact that because we've got 4 spins in our tetrahedron and it's completely random, there's an extra increase in our peak height of this second peak, but that's kind of like an ancillary detail. And so what we found is that we can actually fit this data more accurately if we have, the key thing here is that this delta, this value of delta, this distribution, nicely describes the position and the width. But we can't describe, we miss this area under here. We can fit this distribution a little bit better by taking into account some offset and then some value of 1.5 Kelvin from our previous West bit. And this 0.1 Kelvin that we also is going to the extreme where we think this is the limit with respect to the field, the that we're applying. And we can see that as we apply our magnetic different fields, so 0.2 Tesla and 1 millitesla, we see that we can fit our data. And we can see that in this case, the only thing that changes really is the value of F1 and F2. But when we get 4 Kelvin, there's no change in the values of our fitting parameters. It suggests that we're really measuring the thermal populations. We've shown that we can describe the isolated susceptibility with a very simple Hamiltonian, but as well as driving it with frequency, we can also drive it with temperature. So these measurements, the previous measurements were all done at 2 Kelvin, and if we cool it a little bit more, we go into this frozen regime. And once we're in the frozen regime, you wouldn't expect to see anything because these things are all frozen. But what when we drive into this non-equilibrium regime, we can see that when we go down to 76 millikelvin, without changing the frequency, so all the other data was with changing frequency, without changing the frequency, we can see that our numerous peaks go down to essentially 4 again. Okay, there's these little peaks here, but this is just by changing temperature and not frequency. So we can see that we can drive ourselves into non-equilibrium behavior, and this is no longer determined simply by the Boltzmann population of these levels. So I realize I'm running out of time, so let me just quickly I'll skip this slide and the bulk slide, and I'd just like to show you this isn't kind of limited to dilute spin ice, dilute holmium titanite. We've also remeasured lithium holmium fluoride. So if you remember, this was the original one of the original instigators of this talk, and we found that there were 8 peaks. And again, we see the same difference that we know there's 8 peaks, 1, 2, 3, 4, 5, 6, 7. We didn't quite get high enough in field. But you can see that as we go to higher frequency, so this is the previous data has been measured at 10,000 hertz. As we go to megahertz, we can see that we're reducing our number of peaks to essentially 4 peaks in this isolated limit. So essentially, I think we can really measure the quantum dynamics of state populations using susceptibility if you are careful enough. So with that, I'd like to conclude and say that what we hope we have shown is we can access the single ion limit in the spinous environment, and we can describe this isolated susceptibility. And so we can access an ensemble two-level system, so our spin of our holmium, we can depend on a local environment. The message I take from this is that just by doing a simple susceptibility measurement, it's possible to measure the state populations in a quantum mechanical sense. So with that, I'd like to thank you very much for your attention.
So thank you, Sean. I have a couple of minutes until I need to shoot off. I do have one question, and it how useful is this for sort of quantum 2.0 that everybody's going on about at the moment? You know, you can measure quantum states using AC susceptibility, but you know, is it something that you have entangled state? Is it something that you can actually use?
I mean, it is by, yeah, so if we just go back quickly, but the spin up and the spin out state. And the question is, can you use it? And yeah. I suppose the answer to that is, well, what we have to do now is go down to these, because these are Boltzmann distributed states, right? We have to zero field cool it. We have to pump the levels now to see if we can do it. So in principle, it's a really simple way of measuring state populations. And you have a way of essentially coupling quantum systems together through a magnetic moment in a quite simple way, right? In principle. So it's a lot simpler. If it works, you know, it's a lot simpler than a lot of the techniques that are being done at the minute to store these entangled states. Well, not to store these entangled states, to manipulate these entangled states, sorry. And you by changing the field. So in principle, it's useful. I mean, we started the experiments to use it, Alan, but it's a little, as you can imagine, it's all a bit Heath Robinson at the minute.
It always is, sure.
For those not acquainted with our private English and schema, that means basically built with string.
Put together with gaffer tape. Sure. I do have to go now. I've got another meeting. I'm going to pass over to Evie to continue or whoever it is that's going to continue the chairing session now. Thank you very much. All right, cool.
Thank you, Alan. Thank you, Prof. Yeah, thank you for the great lecture. Any question from the audience? Any question? Okay, so maybe one. More source to
Oh yeah, I mean that's a good question. I didn't really describe it very simply. I mean, the beauty of this experiment is it's incredibly simple. It's literally just two coils of wire, and it's just literally a balanced set of AC coils. So you have a pickup coil and an excitation coil, and the beauty of this is that you can do it just with a lock-in amplifier and a crash. So you can access this quantum state by sweeping the frequency of a lock-in amplifier.
Okay. So actually simple, yeah? Yeah, very deep analysis, yeah, for the simple one. Okay, any other question from the audience?